Good morning. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka, Bangladesh. This is the 15th lecture of the lecture series on X-ray crystallography and solid-state chemistry. I welcome you all in the 15th lecture. Well, I showed in my lecture series, beginning of the lecture series, maybe the first or second lecture, the materials I consult to prepare these lectures are here. Here I again point it out for you that large number of standard books I took, monographs, as well as internet download free, and X-ray crystallography related books, specifically these books: X-ray Methods, Clive Weston, editor Elizabeth Pickard, and publisher John Willey. Similar X-ray structure determination, Stout and Jensen, and crystals and crystal structure, Richard Tilley, and solid-state chemistry and its application, Anthony Arthur West, inorganic solids, Adams, and publications of International Union of Crystallography. I repeatedly say this because this is the sources I use to prepare the lectures for your information. Well, in the 14th lecture, that is the last lecture, I discussed about the device-sharer X-ray powder method and also showed device-sharer X-ray powder patterns of few metals. For example, this one, I can again mention it, that you see that A here, it is a copper metal, it's a device-sharer pattern. B is a tungsten metal, its device-sharer pattern, and C the zinc, its device-sharer powder pattern. We will talk about this structure later, but just to name it now, that copper crystallizes in face-centered cubic structure, tungsten body-centered cubic structure, and zinc hexagonal closed-packed structure. And the experimental data taken is copper radiation, and camera diameter, device-sharer camera diameter was 5.73 centimeter. Well, other than device-sharer, there are commercially available many other techniques to record X-ray powder patterns. Guinea focusing camera and Guinea Heg focusing camera, powder diffractometer, very many commercially available powder diffractometer. In the next few slides, principle of focusing camera and powder diffractometer, powder patterns of materials recorded by different cameras and diffractometers, evaluation of powder patterns, etc. will be discussed. Maybe we cannot finish in this lecture. We have to take another 2 or 3 lectures on powder patterns. Okay, next slide is focusing of X-ray, theorem of circles. That's what is we have to talk now. You see, we know now that disadvantage of device-sharer cameras, that the incident and diffracted beams are divergent, and therefore it has got diffraction beams has got low intensity. But in diffractometers and focusing cameras, a convergent X-ray beam is used. This gives a dramatic improvement in resolution, and because much more intense beam may be used, exposure times are greatly reduced. It is not possible to focus or converge X-rays using the X-ray equivalent of an optical lens. Instead, we made a certain geometric properties of a circle in order to obtain convergent X-ray beam. This has been shown here, this circle here, okay. The arc XY, X and Y, a part of the circle. So if you're at a part of a circle, then all angles subtended from this arc must be equal. That means if we have x, c, a, o, y, x, c prime, y, then y, x, c, 2 prime, y. These all angles are same. Suppose we have the X-ray source here in X, and then X-ray, that means XC, and also XC C prime represents the extremities of divergent X-ray beam emitted from X. If the beam is diffracted by a sample, let's say by a sample which covers the arc CC, this one, C prime, then diffracting planes are tangent to these circles, and the diffracted beams represent X, CY, and C prime Y. We'll focus to the point Y. The principal focusing method is therefore to arrange the source of X-ray, sample, source of X-ray, sample, and detector all lie on the circumferences of an appropriate circle. And that is what is theorem of circle. And we will see that this is being used to construct linear focus camera. Next slide. You see, original powder diffractometer, the original one, what we are talking about, original one. Wait a minute, please. A minute, please. Sorry for that. The device sharer, the original method, which is now a little bit used, and you see, used, and nowadays almost no use, but more modern methods operates on the same principles are used. For example, is Guinea method. Convergent intense incident beam is used, and what I said, and thereby you get an excellent resolution, and the exposure times becomes, sorry for this, what is this? And I'm sorry for this disruption. Okay, the arrangement of focusing Guinea camera, which uses a crystal monochromator M. Here is a crystal monochromator M. That's a source of X-ray, crystal monochromator, and then X is the sample, and it exactly follows the theorem of circle, what we mentioned a bit earlier. This is how what we can see a little bit more focused. You see, fine focused X-ray source, and then we have a bent monochromator crystals, and then has samples, and we get convergent diffracted beams, and here we have placed the photographic film, or we can take this convergent diffracted beam in a CCD detector. Well, this is what I have said a little bit ago, and then we can see a convergent beam of monochromatic radiation passes through the sample X, and sample X that is passes through the sample X, and then this is the radiation is diffracted, comes at focus at A, which a beam stop, and is placed in front of the film to prevent its blackening. Various beams diffracted from the sample, that B, C, etc., diffracted from samples, etc. And we know that theorem of circle A, B, C, X must lie on the circumference of a circle. A, B, C, X, O. The scale of the film is linear in 2 theta and schematic linear powder pattern. Expect that instead of peak of a different height and intensities, line intensity is not here. This is a schematic diffractogram of a sample. Whatever sample it may be, just it is a schematic diagram. One thing is that this intensity, what we measure, can be measured visually or can be used micro densitometer to measure it. If we estimate it visually, then it is not, it's a qualitative one. A micro densitometer can gives us the more quantitative intensity data. And as I said, the sample, we have very little sample is required. It's less than 1 milligram, and exposure time between 5 minutes to 1 hour. And depending on the factor of scale, such as crystallinity and sample, the presence of or absence of heavy elements which absorbs X-ray. Okay, then we go. Now I'm summarizing this detail of Guinea camera's working principle. We have a focused X-ray source. We say that's a focused X-ray source, meaning that X-ray are collimated and focused to a small spot, and enhancing the diffraction pattern's intensity. And then vacuum chamber. We have a vacuum chamber where we'll place the camera, operates because of not to minimize the air scattering. And diffraction pattern, the focused X-ray interact with the crystalline powder, causing X-rays to diffract or scattered in specific direction, creating a diffraction pattern. How we record the diffraction pattern? We either can use image plate, or we can use film or a CCD detector. And then getting the pattern, we analyze the pattern and see determine the crystal structure from and other properties of the powder sample, of course. Well, what I show here in these slides and next two or three slides, that this is the upper one, A, is the diffraction pattern of silicon using by device sharer camera. The lower one is the silicon. You see, in the upper one, exposure time was about 3 hours, and in the lower it's only 15 minutes. Moreover, in here we need to have a capillary tube and put more sample, and here is about 1 milligram or less than 1 milligram sample. You can see how clearly we see the line position and how well resolved it is compared to device sharer camera. If we take the next slide, you see that it's a clumsy, almost a clumsy pattern of device sharer pattern, and it is 8 hours exposure time, and it is a black phosphorus sample. And here by Guinea focusing camera, the exposure time is 30 minutes instead of 8 hours. So we take another example, beryllium chloride, hydrated beryllium chloride. You see, this device sharer camera almost say nothing to us, and this is very difficult to evaluate the film if we take this device sharer pattern of beryllium dichloride, hydrated beryllium dichloride, and even if we expose it in 6 hours. But the same what we are doing with Guinea camera, it's about 90 minutes exposure time. You get a better resolved pattern. More here it's uranium oxide. I said that depending on element in the sample, the heavy element gives us better resolved intense peak. So here it's exposure time 4 hours compared to device sharer camera 30 minutes, and it is also rather well resolved. This one is much more well resolved than that of device sharer camera. Well, then we have to have how to analyze the diffraction pattern of materials, the identification, unknown crystalline materials to identification. We have a very valuable reference source for this, and that is what we call a powder diffraction file. Here it is, powder diffraction file. It is International Center for Diffraction Data. That means in short it is ICDD. It is in USA, and before that powder diffraction file we used to use ASTM or JCPTS file. So now X-ray powder patterns of materials, almost more than 300,000 materials powder pattern is recorded in powder diffraction file for references, and the new entries are coming up almost, say, about 2,000 per annum. So what we have to see from that card, we'll talk it in later slide, but one we can see here that the intensity is the one which we have to look very much, and specifically in this card the first 8 lines in the XRD pattern of in order of decreasing despacing, we identify these unknown materials, but then we have some limitations to identify the unknown materials also that we have to remember here also. The first limitation, if we do not have this powder pattern included in powder diffraction file, then it is very difficult to identify unknown materials. Well, if the material is not pure enough, then we get more extra lines for which it is difficult to identify also. And with care, however, a mixture of crystal materials can be identified with care. If the materials belongs to a family of phases with very similar XRD patterns, it is also a little bit unambiguous. It is not possible to identify properly. That is also a limitation. For example, lithium niobate and lithium tantalate do have almost similar pattern, so it is very difficult to identify compounds related or similar to lithium niobate and lithium tantalate. And also there are some rare earth compounds which is difficult to identify. But the powder diffraction file is a very important file for a very important source to use for identification of unknown crystalline materials. Well, in the next lecture, that's what I'll talk in the next lecture, giving a little bit detail about diffraction file, what we look for, etc. So we look forward to having the 16th lecture where we will talk more about X-ray powder diffraction patterns and how to analyze this and what are the difficulties, advantages and disadvantages. We will talk about it in next lecture. Thank you very much for your attention. Thank you.